again on the spark chamber. And this time I'm taking it much more seriously, and I'm trying to really figure out ways to make it be a permanent museum, reliability piece. I don't care about the looks. I just want it to work forever.
Mm-hmm.
And that's really, really hard to do. We'll get to that later. I want to start by telling you about cosmic rays and what they are and so on. So what is a cosmic ray? So the sun and stars and so on have a corona around them. And out of that corona you get the solar wind. You get the corona is an extremely high temperature, and the protons, the hydrogen nuclei, and electrons get pushed out, and they fly out into the solar system, and eventually they try to work their way out into interstellar space. Now these are protons, right? They are the nuclei of hydrogen. They have a positive charge, and because they are charged, if you have any charged particle, it could be an electron, a proton, anything. If you have a magnetic field that is changing around it, it will feel that magnetic field, and the magnetic field will push it, will accelerate it. And the fields of the sun, they accelerate the protons all the time. You have the fields coming out of the sunspots, and they loop around and they come back, and then these fields sometimes get tangled up because of the differential rotation of the sun, and that causes the magnetic field to tangle, and then they'll get untangled. All of a sudden they'll snap and untangle, and that's a sudden change, and you get these flying protons as a consequence, and they hit us, and we get geomagnetic storms, like a few days ago.
Mm-hmm.
Yeah. So now that's just locally, but you have protons that are being accelerated throughout the galaxy, and some of those protons are, they're accelerated to unbelievable speeds, and those are the ones that I'm going to be really focusing on, and these are the ones I call, these are real cosmic rays. When these super high energy protons come in to the Earth and they hit the upper atmosphere, they hit an oxygen nucleus or a nitrogen nucleus, and they'll smash it to smithereens, and you'll get all kinds of particles coming out from that collision. We call those the secondary particles. And there's many of them. So we say that there's a cascade or a shower of these secondary particles. And some of these secondary particles make it to the ground, and that's what the spark chamber is showing us when it works. So I'm going to show you a video. Let's see if I can bring this up. There, oh, a beautiful one. Another beautiful one. I'm so happy. Yeah. Oh, another one.
The entry point, maybe they aren't close to the plates yet. All the go on the base and have to come up.
Oh, another one. Another one. Another one. So I'm getting excited when I see a row of sparks, and oftentimes they're at an angle. So if we could just get it to not arc on the insulators, I think we are in business. It's a matter. When was the last time these insulators were replaced?
Well, I guess when I was out,
and then they install them.
Maybe the materials. Well, it's not the right.
Okay, I think we're good there. So you see, there are quite a few just random sparks, oftentimes on the edges there where the insulators are. And the problem with the insulators is that they're made out of lucite, and it's a hydrocarbon. And if a spark passes past it, it'll fry the lucite, and the hydrogens leave, and you're left with carbon.
Huh.
And carbon is a conductor.
Mm.
So we're little by little, you're getting conductive paths on the insulators. And so this is the making good insulators is one of several big problems, big challenges for the spark chamber to make it really work. I collected some I took these from the video, and so here you've got one that's going at a nice angle. So, now these cosmic rays, they come from all possible directions, right? The only, there is a slight preference for north or south at lower energies because of the magnetic field of the Earth. We're somewhat shielded towards the equator. But at these energies, it's completely random. They're coming from everywhere around us in the galaxy, and this was a big mystery, is where do they really come from? And unfortunately, if you follow the path of these cosmic rays back, you're not really going to see where it came from, because the cosmic rays are positively charged. They are flying through magnetic fields that are throughout the galaxy, and a charged particle going through a magnetic field will curve.
Right.
And so they curve and curve and curve, and it completely randomizes the direction of travel of these cosmic rays. Here's another one. And here's an interesting one. You see two forks, two tracks really. So my interpretation is that the cosmic ray hit something up here and either bounced off or smashed a nucleus. And so now you've got two tracks where there were, whereas there was just one to begin with. Here's another example of that happening. Okay, so I want to go through the life of a cosmic ray, a high energy cosmic ray. So, so we already talked about the birth, so to speak. You get streams of hydrogen nuclei coming out of stars. Also, if you have a nova or a supernova, then you have a tremendous amount of energy there, and you'll get a huge burst of protons being emitted from those. Now those protons are still kind of low energy. They wouldn't make it very far into our atmosphere, but somehow they get more energy. They get a lot more energy. And the question that everybody was asking is, how does that happen? What is there in space that could take a proton that's moving and make it go faster and faster and faster? And Enrico Fermi, way back in the 30s, I think, he came up with an idea which we now call Fermi acceleration. So his idea is that we have magnetic fields in the galaxy, and the proton that's coming along, when it encounters a magnetic field, it can just reflect back. We call this a magnetic mirror. So the proton can just do a U-turn. Okay. And then we know that the magnetic fields are moving, because a lot of times the magnetic field is attached to some moving plasma moving around in the intergalactic space, where the plasma could be pushed by a supernova explosion. So we can have a magnetic field here and a magnetic field here, and just by random luck, they might be moving generally towards each other. So we have a proton that starts here, and it's moving, sort of slowly, and it hits this magnetic field, but this magnetic field is like a mirror moving have you ever done this? I mean, if you have a ping pong ball and it hits the paddle, it'll just bounce off. But if it hits the paddle that's moving that way, it'll go back with more speed, right? You can even do that with two paddles and get the ping pong ball to accelerate it between the two paddles. So here is the analogous thing going on with magnetic fields. So now the proton's going fast towards this magnetic field. Another mirror is happening and it's moving in this direction. So it's going faster and it hits here and it's going faster and faster and faster until finally the turn radius gets bigger and bigger as the proton gets faster and faster. And at some point, the turn radius will be bigger than the overall size of the magnetic field, and it's going to escape. And yes, we call that Fermi acceleration. So it's a kind of a random-ish process because you don't really, it's not like in a human system where we would design these magnetic fields to move. They just are randomly, some of them are moving apart, which would deaccelerate protons, and some of them happen to be moving together, which accelerates them. And so, because it's a random process, we have many, many protons at lower energies. Okay, so this graph here is showing the frequency of protons at an energy equal to or greater than whatever is here. So we have 1 billion electron volts of energy. Here we have 10 to the 11. So it's going in factors of 100, 100, 100, 100. And, okay, and then up here, going up and down, going up, this is the rate at which you find these protons and hitting the upper atmosphere. So here, 10 to the 0 is 1. So right here, there at this energy, at 10 to the 11 electron volts, we expect to find 1 proton per meter square per second, right? So here I am in an airplane at the top of the atmosphere. I'm 1 meter squared, more or less, and I'm getting hit with 1 proton per second with this much energy, or higher, actually. I did some math at home. That I was having fun last night doing this. I figured out the kinetic energy of a mosquito, and it turns out to be 0.00013 joules. There's an extra J for some typo. And converting that, I get 7 times 10 to the 14 electron volts. So that is here on the scale. And I did the same thing for a 60-mile-per-hour baseball, and 52.9 joules, and I get 3 times 10 to the 20th, which is here. So this is kind of remarkable. We actually detect protons with the energy of a fast baseball.
Wow.
Right? I mean, think about that. It's this little nothing particle, but it's been accelerated so much, it's got that much energy. That's really mind-boggling. And even now, people don't quite understand how that happens. Mother Nature is doing something that we just don't really understand. Okay. So in the upper atmosphere, I think I already said this, but I'm saying it again, the protons hit the nuclei of the nitrogen molecules, the oxygen molecules, sometimes the hydrogen, right? There's water in the atmosphere. And so we're at step 3 here, impact, they hit that. And when that happens, we get the secondary particles, which I kind of already mentioned. Go into a bit more detail here. Now, I want you to remember something. There is this famous formula, E equals mc squared, which is telling us that if you have some mass and you can set up the right reactions, you can turn that mass into energy. And I mean, so in a nuclear power plant, you're doing that. You've got this pile of nuclear material, uranium, plutonium, and you set things up right, and the mass of that uranium gradually gets to be less and less and less. And as that happens, you know, a milligram here, a milligram there, you get lots of energy coming out. The opposite is true also. If you have lots of energy, I'm going to turn it around, you can use that energy to create mass. And so yeah, you can go in either direction. You have to have the right circumstances, but either thing can happen. Now, the proton, which is coming from outer space, it has tons and tons of energy. And I got this diagram out of Wikipedia. It's not perfect for my use here. We're actually, for the Griffith Observatory spark chamber, we're talking about energies a lot less than 10 to the 15th. So actually, for Griffith Observatory, we're talking about energies around here. Oh, by the way, for humans, to make a proton with that much energy is tough, right? You take let's say you have a proton and it's just sitting there, and you put it between two plates, and the two plates are, let's say, 1,000 volts apart in difference. You have a 1,000-volt battery. The proton will start moving because it's attracted to the negative plate, and by the time it gets to the negative plate, it will have 1,000, right, 10 to the 3 electron volts. Right. Okay, so you can do 1,000,000 volts. You can have a plate here and a plate here with 1,000,000 volts across. That'll get you to 10 to the 6. But 1,000,000,000 volts, no, that's not feasible. And so in order to achieve 1,000,000,000 volts, you have to circulate the protons and have them go through these plates, which are alternating in voltage, and each time they go boosted, 1,000,000 volts, another 1,000,000, another 1,000,000. And if they go around 1,000 times, now your 10 to the 6 volts is 1,000,000,000 volts. Yeah. And the limits of our human accelerators are somewhere around here. Even CERN can't beat Mother Nature. Okay, so anyhow, going back to here, we have a proton with a lot of energy. For us, not really 10 to the 15th, but it's okay. And it hits something, and suddenly, when the quarks, when the innards of the fast proton encounter the innards of the target, so to speak, the victim, whatever it is here, a proton or a neutron, you suddenly have a flash of energy, and they call it a quark-gluon plasma. And out of that, you can make all of the possible particles within the limits set by the amount of available energy. And so you have so much energy, right? One proton is only 10 to the 9th, electron volts. So you could be making more protons, right? They're showing that you're making more protons here. You could be making pi plus particles. Okay, so pi plus particles are here. Maybe we can turn a little bit of the lights back on. They have an energy, they have a mass. So if you have 139.6 MeV over C squared of energy available, which is not a whole lot, for cosmic rays, you can make pi pluses and pi minuses. You can also make muons and anti-muons. The energy needed for a muon is 105.7 MeV over c². So MeV, by the way, is 10 to the 6 EV. Right? And here they have 10 to the 15th EV. So there's a lot of 10 to the 6s in 10 to the 15th. So there's plenty of energy there. And, okay, so coming out of this initial collision, they're showing a proton that's been created, a neutron that's been created, a pi plus particle, a pi minus that's been created, a pi zero that's been created. And so you get all these different kinds of things happening. The pi zero creates an electron shower, an electron, anti-electron shower. So the E minuses, those are electrons. The E pluses, those are anti-electrons, also known as positrons. So for us, what matters for the cosmic ray, the Griffith Observatory cosmic ray chamber, this is what matters. The pi minuses that become muons, and the pi pluses, they put extra extra stuff here, but you could get easily pi pluses coming out, and those will also make muons. These will make, this is an anti-muon. The pi plus is an anti-muon. Okay. One thing I didn't like about this picture is that it shows the products like coming out at like 90 degrees, which is totally wrong. They did that in order to just fit it on the page. Right. In real life, here comes the proton, and you get this shower pretty much in the forward direction. In this simulation, something came out at 90 degrees. It's not clear, what it was, but this is much more realistic. You get a forward beaming cascade of lots and lots of particles. Okay, so continuing. We have these pi minuses and pi pluses. Now over here, I've put, besides the mass, I've also put the lifetime. So for the electrons are forever. I put infinity. And then over here, protons, they're also forever. It's infinity. But pions, they don't last very long. Micro is a millionth of a second, so they only last 0.026 microseconds. Muons, they last quite a bit longer, 2.2 microseconds. Then, now this is actually a very long time because this doesn't prevent the muons from getting to us. Yeah?
What do they convert back into something? When you say they don't last, they can't just disappear, right? So do they become a different particle?
Right. So a mu minus will disintegrate and produce an electron and a muon neutrino and an electron antineutrino. Huh. So you'll see the electron, but the neutrinos, they're gone. They just leave.
So they're so non-interactive?
Right, yeah. So it's very, very difficult to get a handle on the neutrinos. Okay, so where were we? Yeah, so the pions decay very quickly, and so we don't get pions at Griffith Observatory. But we don't get the pions, yeah, they decay too quickly. But we do get muons at Griffith Observatory. Huh. Now, if you were to work it out, right, the speed of, these particles are going at practically the speed of light. Right? So a microsecond is the speed of light is roughly 1 foot per nanosecond. Right? So in 1 nanosecond, 1 billionth of a second, a photon will go from here to here. And a muon, pretty much the same. Now, a microsecond, that's 1,000 nanoseconds. So in 1 microsecond, the muon will travel 1,000 feet. In 2 microseconds, it'll travel 2,000 feet. In 2.2 microseconds, now 2,000 feet, wait a minute. The muons are coming from, 20 miles up. That's way more than 2,000 feet. Okay, students, what gives? How does the muon manage to not disintegrate in 2.2 microseconds? It actually gets all the way to here and beyond. Okay, yes.
Time dilation.
Time dilation, yes.
Relativity.
Time slows down when you're going near the speed of light. And so, yes, if the muon were stopped, it would disintegrate in 2 microseconds. But it's not stopped, it's going near the speed of light, so time slows down for the muons. And that gives them plenty of time to get to Griffith Observatory and below, that go right through the observatory. Okay, so, all right, so anyhow, let's see. The pi minus will decay quickly, right? It's really fast decay. So it decays into a muon and a muon antineutrino. And this is a chemistry style formula. You got pi minus going to a muon and a muon antineutrino. Okay, so now these muons are in play. The muons, the mu minus and the mu plus, they still have a lot of energy, and they're going close to the speed of light. And now, the muons, they are just like electrons. Electrons are point particle. They have essentially zero cross section, and they have an electric charge. And the muons are the same way, but they are 200 times more massive. So, if it was an electron with that much energy, as it comes down through the atmosphere, the electron would eventually hit another electron, and the kinematics are like, pool ball hitting pool ball, and when you do that over and over again, you dissipate the energy. The energy will be spread out among all the pool balls, or all the electrons, and the electron will very soon stop. However, the muons being so heavy, it's more like a cannonball going through a lot of marshmallows. It just keeps going and going.
It's messy.
And so they slow down. I mean, I'm not saying they go forever, but they slow down very, very slowly, and that allows them to make it to the ground. They have enough energy to plow down through the atmosphere, through the concrete. They go through the roof, through the floors, and through the spark chamber, and they keep going.
And through us.
Now, I threw this in. It's an interesting fact that at accelerators, they make lots of muons. And there are these interesting experiments where the muon knocks an electron out of, away from a hydrogen, and the muon goes into orbit around the proton. And now you have a kind of hydrogen, except instead of a proton and an electron, like normal hydrogen, you have a proton and a muon orbiting around it. It doesn't last long. After 2 microseconds, it's gone, but yeah.
So typically when we're thinking about these particles coming through the atmosphere, we're thinking atmosphere above us come down to the surface. But
Right.
if they can go through material, then they could also hit the atmosphere on the southern hemisphere side of the Earth and go through the Earth? Or would they have not been able to go through that much Earth to get?
Well, the muons are, after a few miles down, then they, as penetrating as they are, they have their limits, and they stop. The neutrinos, though, they keep going right through. Okay, so keep going. So here we are, Griffith Observatory, Hollywood sign, here comes our muon, and it goes through the spark chamber, zap, and eventually it'll stop and it will, maybe a few thousand meters below ground, it'll stop and go poof. Yeah.
And from there, the electrons go however far they go.
Well, at that point, the muon has slowed to essentially to a stop, and the electron will have some maybe 2/3 or 90% of this energy. It'll have 100 MeV, but 100 MeV isn't going to take the electron very far,
right.
And it'll just get absorbed by whatever chemicals are in the rock. Yeah. Okay. So, the muon, when it finally stops, it's going to decay, and it'll turn into an electron. If it's a mu minus to begin with,
right.
It'll turn into an electron, and we actually said this earlier, because you asked the question, and into a muon neutrino and an electron antineutrino. Yeah. The neutrinos keep going through the ground, out the opposite side of the Earth, and they leave the solar system. And the electron stops and is absorbed by the rock.
You have a question?
We have a question, yes?
Is this like a similar process to the Northern Lights? Or how does that happen?
So for the Northern Lights, we would be backing up to, I guess, to here, right? So forget about everything that happened down here. It's just the protons hitting the upper atmosphere. And those protons are coming from the sun, and they have energy, but they don't have nearly as much energy as we're talking about here. But they have enough energy to make the atmosphere glow. And the Northern Lights are not only caused by the protons hitting the atmosphere, but they're also caused by the electrons, because there's both coming out of the sun, both electrons and protons.
And we don't see this kind of effect from electrons because they aren't massive enough, they don't have enough energy?
The electrons, so we're talking about protons here that came from halfway across the galaxy.
Mm-hmm.
And I think what would happen if you were to have an electron with that much energy, it would interact with dust or molecules and so on in the interstellar medium and be absorbed. Having said that, there is a kind of there's what we call gamma ray observatories, and they are interested in the, you can have, you see, an electron, when it hits something, will make gamma rays. And so you could have electrons, like halfway across the galaxy, hit something with a lot of energy, make gamma rays, and those gamma rays will keep going in a straight line.
Right.
They won't get randomized like the cosmic rays do. And they'll go in a straight line, and eventually the gamma rays hit the upper atmosphere, and you get the continuation of this shower. And there are telescopes that look for this type of shower. And so the gamma ray telescopes they were built because there's a hope that we could identify particular sources in the galaxy. Yeah. Okay. So where are we? Where are we?
Yeah.
Oh, okay. So cosmic rays death. So we followed the negatively charged version of the cascade, but there's also the positive version of the cascade. You can make, there's enough energy to make everything. So the proton makes pi pluses as well in the collision. And the pi plus will decay to a mu plus, right? This is an anti-muon, and a muon neutrino. And the mu plus behaves just like they view minus. It just plows through the atmosphere like before, and eventually it stops and it decays. And when it decays, the positive muon will turn into a positive electron, a positron or anti-electron, and a muon antineutrino and a muon, an electron, neutrino. By the way, there's a method. You might think, oh my God, Halverson knows so much, but there's a cheat. Okay, I'm cheating a little bit. I know the trick as to how to figure out the neutrino thingies coming out. The trick is lepton conservation. So if you know the rule, then this becomes super easy, and I can explain that later if you like. Okay, the anti-electron will meet a normal electron at the end, right? The muon decays into the positron. The positron will eventually meet up with a electron, and when they touch each other, they annihilate each other, and you get two gamma rays coming out. The gamma rays, by the way, happen to have exactly this much energy, each one of them.
Huh.
And that's law of it's sort of the expanded law of conservation of energy, right?
Sure.
It says how much energy is in the electron. Okay, well, the gamma ray has to have that energy. And then of course the photons don't go very far and they're absorbed. The photons cause a slight increase in the temperature of the rock. And then I put there, but wait, what about the neutrinos? That's just a teaser, you know. Of course, they come out the other side, and that's a whole topic in of itself.
Next semester, right?
Yes, right.
Maybe they light up a light bulb in a giant underground flooded chamber in a mountain in Japan.
Right, right. Okay, so now let's talk about what's going on at the Griffith Observatory spark chamber. Right? So meanwhile, back at the spark chamber, we see a series of sparks. How does it work? Now here's a picture from a long time ago, actually, of the setup. This was 15 years ago when it was actually the first time I got it working. And you've got a stack here. Number 6 is a stack of aluminum plates. And that's what you see, you know, in profile.
Okay.
If you go back to, so this picture, each one of these is an aluminum plate. And the sparks are jumping between the aluminum plate.
Is there a reason it's aluminum specifically?
No, could be copper or whatever. Aluminum is easy to machine. I labeled one, there's a 1 here and a 1 here. These are the scintillation detectors. I'll talk about this a little bit later. But they detect that a muon has gone through. And number 2, these are called discriminators. The problem with these scintillation counters is they also detect random radiation things. And so the number 2 discriminates against that. And then number 3, it's called a coincidence unit. It waits for 1 and 1 to see something at the same time, basically. So if you see something happening here and here simultaneously, then you know something happened, a muon happened,
Okay.
or some charged particle. The coincidence unit goes to this big box, which has this scary, lethal power supply, these big capacitors inside. The capacitors are charged by this nifty high voltage power supply, which I'll dial up to 15,000 volts. And so this box is waiting, the capacitor is waiting for the signal from the coincidence unit, and when it gets the go, it dumps the capacitor into the aluminum plates, and you get those sparks. Same thing here, but more diagram-ish. We have the scintillator here. You see I put a little flash here. That's because when the muon goes through, there's a flash of light. The flash of light goes to a photodetector called a photomultiplier tube.
Okay.
It's an old style stuff. It's still the best.
Wow.
You can't really replace photomultipliers in this job. The photomultipliers see the muon, but they also see lots of random radiation things, you know, because we've got radiation all around us from the rocks and so on. And but they clean up. The muons make a big flash, so the discriminator keeps the big signals and tosses out the little ones. The signal comes to here, to essentially an AND gate, a logical AND gate. And we have the same process happening below the chamber, and it sends its signal to the AND gate. And when you see a signal in the upper detector and in the lower detector, then we call that a coincidence. The coincidence circuit sends the trigger signal to the high voltage pulsar. The high voltage pulsar dumps that charge into the plates. From an electrical engineering point of view, this is kind of interesting. Every other plate gets the high voltage. Those are the black ones. The green ones, green is ground for me, and so they stay at 0 volts. They're connected to ground. So you'll get a high voltage spark going from black to green, from black to green, black to green, and so on. Like that. Zap, 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 zap. Okay. Now, I drew here a box around this thing. The box is airtight, and it's filled with a noble gas. We're using argon, which is inexpensive because the welders use it.
Yeah.
So you can get argon really cheap. I'm scratching my head about that. I have a feeling that if we were to use helium and neon, it might work a little more easily. It might get rid of some of the problems I'm having. Did someone have a question?
I was gonna ask like what other gases can you use?
So it has to be a noble gas. It has to be one of the, we have, over here. Could be any of these. Helium, or neon, or argon, or krypton, or xenon. Could even be radon.
You're not going to use unobtium?
Radon would be good.
What is that?
Unobtium.
Unobtium. I don't know. That is.
How do you know what that is?
How do I know what that is?
Yeah.
Or how I... A, it's up there. B, I read the article when they announced that they discovered it.
Periodic table before you go to bed every day.
Is it a gas?
I don't know that it existed in the lab for long enough for them to identify a phase of it. They made like a couple atoms of it, and then it decayed.
Well, the good thing about
They
argon
found enough of it
is that it's
to know it
super
exists.
cheap. But the thing is, though, that it's a little harder to make a spark in argon than it is in helium.
Oh,
So
yeah.
if we were to replace the argon with helium, it might relieve some of the pressure on the performance of these electronics. Because going to a lower voltage might help. So
And
it's
if you
something I'm
suspected
thinking
you
of.
had any leaks, you could just put your head next to it, and if your voice got really high pitched,
So there were some, when we were watching the video, there were some sparks that were not cosmic rays.
Right.
So something is still triggering the mechanism to send the charge into the plates then for those?
Okay, so I wanted to save this for later, but
I'll find out later.
okay. Yeah, that's a very, very good question. Okay. So anyway, I think I went through all of this. Let's keep going. And I explained that this is what I just said in words. The muon makes a flash of light. The scintillators are clear plastic. I put some. The light goes to the PMT. You get a flash. PMT needs photomultiplier tube, and it's super sensitive, and it's very fast, and the fast part that has to do with your question. Speed is important. The PMTs make the pulses, and then, okay, we have radioactivity that confuses things, but we have the discriminator that tosses out the small pulses, and then the discriminators go to the coincidence unit, and if you get a pulse from both of them at the same time, that's an AND function, then you get the trigger pulse. The trigger pulse goes to that big deadly box, which has capacitors charged to 15,000 volts, and then so the trigger causes a dump of the charge into the aluminum plates. And the black plates are suddenly at 15,000 volts, the others are at 0, and so if 15,000 is too much for air, and so you will get sparks regardless.
Right.
But what we want, this is something new. So when a muon, when an electrically charged particle goes through air, it ionizes the air. It knocks electrons off of the air molecules. So now you have negative electrons in a cloud, and then you have positive ions in a cloud, and then that gets hit with a big electric field, and it causes the electrons to rush towards the positive plate, and the ions to rush towards the negative plate. And that sudden motion causes more ionization. You get a kind of what we call an avalanche effect, or like a domino effect, where ionization creates more ionization, which creates more ionization, and so then you get the spark. Okay. And yes, the air is somewhat conductive, a little bit more conductive than in other places, and that's where the spark occurs. So, okay. All right. So, any questions as to how the thing works? Yeah.
I think just my question is, like, when you are seeing the spark that's traveling between the plates, obviously,
Right.
like this particle is moving incredibly fast. So what you're not actually seeing it necessarily like in real time. You're just seeing like this was the path that it was taking as that like avalanche effect is kind of like triggering between them.
Right.
Okay.
Yeah.
I guess that wasn't really much of a question, but just if you could, I guess if you could just confirm my understanding.
Yeah.
Okay.
Yeah. So, and what your question asks relates to Jessica's question. So, here's the thing: the ions that are created by the muon passing through, they don't last forever. They get reabsorbed by whatever gas you have in there. And if it's a noble gas, they're going to be reabsorbed in 500 nanoseconds.
Yeah.
Okay. Now, actually, that 500 nanosecond number, I can't figure out where it came from.
Huh.
I went to the MIT website, and there's this professor who says it's 500 nanoseconds. And there's another guy, it's 500 nanoseconds. But where, nobody,
Why?
somebody must have done a bunch of spark chamber constructions, and some of them worked, and some of them didn't work. And they found, well, if you turn on the high voltage more than 500 seconds after the muon went through, it doesn't work.
Huh.
But if you turn on the high voltage before 500 nanoseconds go by, it works. Now, we get to Jessica's point. There are a lot of places, a lot of times when there was a spark, but no track. Now, I can pretty much guarantee you a muon went through. The problem is, the spark didn't develop, the high voltage didn't get turned on until maybe a microsecond or 1.5 microseconds. So by that time, the ions got reabsorbed, and so then there was no ionization trail to follow. It was gone.
We're just picking up the end of its path.
Right. And so this is something that I'm actually kind of scratching my head about. Why does it even work? Right? It's way more than 500 nanoseconds, and yet it does work some of the time. And the question is why? And so obviously the ions don't disappear, like exist, and then at 500 nanoseconds, poof, they're gone, right? It's a chemical reaction of sorts, and so it's an exponential decay in ion concentration. So maybe we're just getting lucky, and we're seeing picking up the tail of the decay curve, the concentration of ions curve. That's one possibility. Now there's another possibility. It turns out that a charged particle, when it's going really fast, doesn't disrupt air that much. But as it slows down, the electric field of the muon has more time to bother the molecules. So a very, very fast muon, we call that a minimum ionizing particle when it's going close to the speed of light. But as the muons slow down, they become more disruptive to the air, and they'll create more ions. And actually, just before they come to a stop, that's when they are maximally ionizing. And so, so maybe that's what's going on. We're picking up the muons that were going really fast and just kept going, 1,000 feet below ground. Those are the ones that cause kind of random-looking triggers, random sparks. And then the muons that were slowing down and maybe were just about to die, those are the ones maybe that are causing a real track. Maybe. I tried to kind of do some little experimentation with the spark chamber, but I wasn't able to really find evidence supporting that hypothesis. But I don't know. Yeah. So, in terms of the problems of making this thing work reliably over a very long time, when you're designing electronics, when you want speed, when you want something to trigger within that 500 nanoseconds, you need to have small parts, because big parts have lots of capacitance, and that slows everything down. And so I go to the part supplier, and I get the fastest possible transistors that are, now, finding fast transistors that are rated for thousands of volts is tough. And so anyway, I put it together, and it works, tap, 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 for like a minute, and then smoke. Yeah, literally we had smoke one day. And so it's like trying to get a Ferrari, to run and run and run. Ferraris are good for a few hours, and then they need to be overhauled. But there's like this kind of contradictory need, reliability versus high performance. And so finding the sweet spot between those two is sort of what I'm working on.
Materials. That's good.
So, okay. Oh, I have lots of pictures to show you if you want. This is a picture, it's covered with aluminum foil, but there's a big piece of plastic here. And then here is the photomultiplier, and then the discriminators there. This is the photomultiplier. The discriminator is an old style TTL chip. You guys remember TTL logic? Yeah. Oh man.
Sorry.
Okay. Here's the circuit. So you've got the scintillator here, and here's the photomultiplier, and then it feeds into the discriminator, and then it gets, the output of the discriminator is not enough, so I had to add a transistor, and then that goes to the coincidence unit.
In one of the previous pictures, there was a, what was the the prism, the reflecting prism? What is that?
Oh, because the light needs to go into the end window. Yeah, you see, the photomultiplier, its window is here.
Okay.
And so, to get the light to go into the end window, you see the light's coming this way from the plastic,
Okay.
and then it's gonna hit a mirror essentially to go into the photomultiplier.
Okay.
And the mirror is a piece of plastic that's 90 degrees. It's a triangle.
Yeah.
And then this is the 45-degree part of the triangle here.
Neons are coming from all directions.
Right.
So what's,
When a muon hits the plastic sends light in all directions. It's a completely isotropic, all directions glow. Yeah.
So if you had a really fast camera basically watching the inside of that plastic, you could actually see the plastic light up. Like I'm thinking of the, there have been a couple videos where people take like femtosecond frame rate cameras and watch a pulse of light moving through a water bottle, for example. So like if you had something that fast, you know, looking at the side of the plastic, you could see the plastic itself light up.
The thing is that I think the chemical that's in there is not quite that fast.
Okay.
It's fast, but it's not that fast. No. So maybe the chemical responds in 10 nanoseconds.
Sure.
But in 10 nanoseconds, light's already moved 10 feet.
Yeah, yeah.
So you'd get a blur.
Right.
This is the sort of construction for the discriminator and also for the coincidence unit. You know, you've seen these breadboards before.
Yeah.
And these are, this is the discriminator chip, and then this is actually a 555 integrated circuit. I'm using it to make the circuit self-adjusting. The problem that solves is the photomultiplier sensitivity changes over time depending on the temperature in the room and so on. I got a little bit more sophisticated here and made it self-adjusting.
isolate it? Put it in some sort of containment unit where you can stabilize the temperature?
You could, but
That's what the pitch for the increased research budget.
I was talking about a big switch that suddenly connects the big deadly capacitor to the plates. So that's what this is from the user manual for. It's a vacuum tube switch.
Okay.
It's a hydrogen thyrotron. These hydrogen thyrotrons, they're still used. It's hard to make a cheap and effective replacement for it. These things were developed for radar. So in radar, you have, it's a microwave, right? You're sending microwaves out to the airplane, the microwaves reflect back, and you time the pulse, the time of flight of the pulses. So you need to have a short pulse of microwaves. So you use a magnetron, which is the thing inside of a microwave, but it's like turning on the microwave, right? But for maybe 100 nanoseconds. So imagine turning on the microwave for 100 microseconds. So what this thing does is it provides pulses to the magnetron. As the radar's going around, this thing is activating the magnetron, whatever, 100 times per second or 20 times per second. So that's what these were developed for. This is looking inside the pulse unit. Here's the thyrotron tube, and are the capacitors, and then these big fat wires are needed to move the current around, and eventually the cable to the spark chamber connects here and here. So this is the high voltage, and then this is the ground. And I guess that's it. I don't have any more pictures to show you.
Nice.
So.
Yay.
Very cool. Thank you very much.
Yeah.
All right, you're welcome. It was fun. That's cool.
Cool.
So if we go to Griffith Observatory, can we walk over and see the spark chamber? Is it on display now, or
No.
Not
I was
yet?
gonna ask, where on the premises is it?
Well, it's actually in my bedroom.
Field trip.
My office, so to speak, bedroom office. And the stack of, I left a stack of plates at the observatory because it's really heavy and I'm afraid I'm gonna damage it. But I took this and the other electronics home because just commuting back and forth,
Sure, yeah.
it's just a killer commute.
Yeah, it is.
And so I wanted to have more time to be able to really research and think about what's going on in this electronic thing.
How long have you been working on it this second time?
So we started in January, and I thought I would be done with it in like a couple of weeks, and here I am months later. And I worked on it every day for like 3 weeks, but then school started, and I had to start teaching and grading papers and so on. So I kind of had to stop, and I think that when school finishes, then I'll have a chance to really work on it again. I promised to have this done by our field trip, but I don't know that I'll be able to keep that promise. So I think I might barely be able to get it to like limp along, just long enough for my students, come on in, turn it on, boom, 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 and then, okay, turn it off, bye-bye students. Something like that. So make it run for a few minutes.
Cool.
If you go to Griffith Observatory, there is the new part of the observatory,
Yeah.
which has the big room with the big, enormous picture, right,
Yeah.
of the deep space there.
Yep.
And on the upper level, there's the cloud chamber, and next, sort of over a ways, there's the spark chamber, which right now says out of order. Okay.
Yay.
Oh, you have a question? Yes.
The second picture, the one before that,
Yeah.
is that what is going to help the chamber stay on?
So, okay, if you compare this picture to this, you'll see the similarity,
Oh yeah, okay.
right?
Yeah.
So, this is a glass tube, it's been evacuated, so there's a vacuum, and then they put a certain amount of hydrogen in there. And the hydrogen is there, so it's essentially a spark gap. The high voltage is pushing against the gas. And if the gas gets somehow tickled, a little upset, a little ionization happening, then a spark will develop inside and it will let the electricity fly through. That's what is happening. So what I have to do, this thing works great. The problem I'm running into is the part of the circuit that tickles the tube. Tickling requires about 400 volts. And that starts the discharge inside the tube. 400 volts isn't that bad, but once this thing turns on, you have 15,000 volts suddenly rushing around, and you get this incredible electromagnetic pulse, and all the electronics in the lab go like this.
Okay,
The
yeah.
computers reset, the phones do weird things, and stuff inside gets fried. It's like really, really beefy tough stuff.
So you were saying the reason why you need that 15,000 volt power source is because of the gas that you're using. The argon, correct?
Well, so I've been researching, what other people have done, and one thing I've noticed is that all of the other spark chambers that are out there that I can find use a mix of helium and neon.
Huh.
And so I've been scratching my head, why? Argon is so cheap, argon is so good, what's wrong with argon? And so finally, in fact, this was last night, preparing for this actually helped me.
Yay.
So last night I had an epiphany and I started looking up the breakdown voltage for various gases.
Oh.
And it turns out that helium has a lower breakdown voltage than argon.
Huh.
And so my thinking is they're taking advantage of that. And so maybe if I put helium in there instead of 15,000 volts, maybe I could get away with 10,000. That would help a lot.
Just so that I'm remembering my physics terminology correctly, breakdown voltage is when something goes from being an insulator to being a conductor?
Right.
Okay.
Yeah. When the electricity breaks through.
Yeah.
Yeah.
Can you mix argon with anything?
You could mix argon with helium, I suppose, or with neon. Okay, so Wikipedia. It seems like the thing that makes helium break down more easily is that the electrons. So at the very beginning of breakdown, you have, let's say, a stray electron, and the electron feels the electric field, so it accelerates. But if it hits an atom, immediately that acceleration is interrupted.
Right.
But if it doesn't hit an atom and it goes faster, when it does eventually hit the atom, it ionizes that atom too.
Right.
And you'll start to get a kind of a domino effect, a cascade. So the thinking is that since helium atoms are smaller, the electrons are less likely to actually run into them. And so it's easier to get the electrons accelerated and to start that cascade process. So argon atoms are much bigger than helium atoms, and so that.
But it requires more electricity to create the reaction that you're looking for. So argon is just like that sweet spot of like the bright gas with.
Well, argon.
Sorry.
So the way I'm thinking right now, argon is a problem because it requires more of an electric field to get it ionized.
But it's also like the size of the size of the molecules themselves are the right size to get the reaction that you're looking for, like in between the plates to get the zap.
So, okay, these are noble gases.
Right.
So they're not molecules; they're single atoms
Right.
in gas
Excuse me.
form. Okay, so why noble gases? If you were to use, let's say, oxygen or fluorine or something like that, as soon as an electron is made, chemistry is basically electrons getting caught and or released. So it's absorption and emission of re-release of electrons. The noble gases, they don't grab electrons. They just sort of ignore. I mean, in terms of chemistry, what a chemistry teacher would say, the noble gases just ignore the electrons. Whereas, basically everything else, if there's an electron on it, it'll grab it.
Right.
And so if you have oxygen in the chamber, the spark chamber just won't work. So if there's a leak and oxygen or nitrogen or just air gets into there, the spark chamber stops working. You have to have a noble gas.
I guess I was kind of comparing, like helium or neon, argon would be just like more massive. Like,
It's more massive.
So it would get the reaction that you're looking for better than helium or neon, but requires more energy. So it's like argon is just like that like Goldilocks point where it's like it's affordable, it's gonna give you the reaction that you're looking for, but the only downside is just the energy required to actually trigger that.
Yeah, I'm not sure I agree with that. You know why we got argon?
Because it's cheap.
Yeah, it was cheap, right?
Okay, so like
Yeah.
if you're using like helium or neon, you can use less power. But then, I think when you were kind of mentioning was that there was like almost like a triggering mechanism that was like not like fast enough to
Right, right.
but because
Yeah.
it's like you're trying to put too much rush too much power through, and that's why it was burning out. So if you use like neon or helium, you might be able to find the components that you can actually use to run less power through and get more reactions, I guess, or more zaps. Is that my understanding?
If I could get the high voltage down to 10,000 volts,
Yeah.
then maybe I wouldn't have to use this monster tube. Maybe I could use a smaller tube. Maybe then I wouldn't need to have a 400 volt trigger, and so on. You know, there's sort of one thing leads to another, leads to another. If I could scale everything down, then it becomes easier. You would think, anyway. So anyhow, right now, I'm thinking that in the immediate future, I'm just going to reassemble this thing in the way it was in January. It was kind of sort of working. You saw a lot of misfires, but there were enough enough true tracks that it was actually acceptable. I think most people would have considered that good enough. So, all right.
Well, thank you very much
Thank
again.
you.
And please, thank you guys for coming as well.
Absolutely.
And please help yourself to all of the food.
And thank you for the excellent questions.
Yay.
We're hoping to